hypothesis, it means that smoking, represented by three variables, PAX1, PAX2, and PAX3, all have coefficients equal to 0. If that were true, what we would have is just the intercept-only model. So it's comparing a model with an intercept and 3 covariates to a model with just the intercept. That's why all these tests here have 3 degrees of freedom. They're simultaneously testing that all 3 variables, PAX1, PAX2, and PAX3, simultaneously have 0 values for their coefficients. If that is true, what we have is the null hypothesis. The null hypothesis that everybody has the same risk regardless of their smoking. But notice once we fit the model, we get a coefficient of PAX1, we get a coefficient of PAX2, we get a coefficient of PAX3. Those can be turned into odds ratios, just the same 3 odds ratios we had before from the 4x2 table when we compare each of those smoking categories to a non-smoker. So notice now on this table, there's another p-value being recorded, a different chi-squared test. Value of 1.12, 8.09, 0.2086. All of these have 1 degrees of freedom. These are different null hypotheses. These tests are not testing the global null hypothesis. These tests are testing a specific comparison. The 1.1218 is testing the null hypothesis that the true coefficient of PAX1 is equal to 0. Remember, PAX1 is the log odds ratio comparing a 1-pack-a-day smoker to a non-smoker. That's what that odds ratio 1.169 was from the 2x2 table, comparing just 1-pack-a-day smokers to non-smokers, leaving everybody out, leaving the 2-pack-a-day smokers, leaving the 3-pack-a-day smokers out of the analysis. So what these tests of significance are doing on this part of the printout are specifically comparing one level of smoking to non-smokers. This first test is comparing 1-pack-a-day smokers to non-smokers. The second one's comparing 2-pack-a-day smokers to non-smokers. The third one is comparing 3-pack-a-day smokers to non-smokers. Because that's what these 3 odds ratios are comparing. So we could see, for example, there's a significant difference, p equals 0.0044, when we compare the 2-pack-a-day smokers to the non-smokers. There's a non-significant difference, 0.2895, when we compare the 1-pack-a-day smokers to the non-smokers. And a non-significant difference when I compare the 3-pack-a-day smokers to the non-smokers. So these are specific pairwise comparisons comparing one particular smoking level to the non-smokers. So from the same model, we get 2 different types of tests of significance from fitting this model. We get a pairwise comparison, comparing a particular level of smoking to the reference category of non-smoking, and we get a global test of significance to comparing the single entity smoking with 4 different levels to the null hypothesis says that each of these levels have the same risk. So depending on what you're interested in, you'll be looking at different parts of this output for doing different types of significance testing. So finally, let's return to the one other test we did last week, which we fit a model that says, I'll get back, I don't have another model. So let's now move on to the next issue. So to just summarize what we've learned so far, we know that for a 2x2 table or for a 4x2 table, we could do tests of significance, measure odds ratios from the tables themselves, or we could fit models. And for a 2x2 table, there's 3 different tests of significance that are furnished from a logistic regression model. All of them are based on likelihood theory. All of them are based on maximum likelihood estimates. We get an odds ratio, we get a confidence interval, which is exactly the same as the odds ratio and confidence interval we had from the 2x2 table. For a 4x2 table, we get 2 different tests of significance. One is a global test, asking whether the entity smoking itself is a risk factor for developing disease, and the specific pairwise comparisons for comparing different levels of smoking to non-smoking. So knowing that we can recreate a model, what we could do with a table, let's move on and now say, how can we use models to control for confounding? What I'm going to use as an example of that same data set, again looking at the relationship between males, top row being men, bottom row being women, first column being those who developed coronary heart disease, second column being those who didn't. Again, for those who just joined us or weren't around at the beginning, these little F's here are just formatting problems, trying to, in PowerPoint, show the results of a SAS printout. In your mind, just replace all these F's by a straight line. Have that 2 by 2. Again, showing that men have a 25% risk of getting heart disease, and women have a 14% risk of getting it. But now let's suppose we want to control for a potential confounding factor. Remember, we talked about confounding a few weeks ago. Let's suppose age was a potential confounder that I wanted to control for. What I'm going to do is I'm going to take the variable age and dichotomize it into the young versus old. I'm going to break it age at the median age, which was around 55 in this data set. So for the crude 2 by 2 table, the one we're looking at now, that corresponds to an odds ratio of about 2 in this data set. The odds of getting disease if you're a male are twice that of the female. If I go back to the previous table, if I calculate the odds among the men, 164 divided by 469, divided by the odds among the women, 1/4 divided by 616, we get an odds ratio of 2. That's the crude, unadjusted results. What happens if I control for age? What I'm going to do is I'm going to break my data set into 2 groups. People who are under age 55 and people who are 55 or older. So this is the 2 by 2 table just using the 870 young people, people whose age is less than 55. I made a new variable in SAS called age 55, and anybody who was under age 55 had a value of 0 for that particular new variable. So here are the 410 men and the 460 women who are less than 55 years of age. 22% of the men got disease and 11% of the women got disease. So in this table, the odds ratio was a little bit bigger than 2, 2.38. If I look at the older people, the remaining 410 men, the remaining 460 women, and there's a typo here. It says age 55. Back. Okay, here's the original 1,363 people. Here's the 870 young people. And the remaining next table, here are the 493 old people. Right, so here's the older 2 by 2 table. Everybody who was older than age 55 had a value of 1 for that new variable. So here are the 233 older men. Notice more of them got disease. 30% of them got disease. Here are the 260 older women. More of them got disease. 20% got disease. So unlike the previous table, let me go back to the younger table, where the risks were 22% and 11. Now the risks have increased, 30% versus 20%. But again, I can compare old men to old women here. I'll get an odds ratio, which is a little bit less than 2, 1.67, 1.7. So now what I've done is I've divided my data set into 2 pieces. Young people, comparing young men to young women, get an odds ratio of around 2.3. And I compare old men to old women, get an odds ratio of around 1.67, 1.7. Both of those comparisons hopefully are free of confounding. Because in the first table, I'm comparing similar age men to similar age women. Young men versus young women. And in this table, I'm comparing similar age men to similar age women, older men versus older women. So what I'm using here is a method called stratification to control for confounding. What we do is we break our data set up into pieces. One piece being made up of young people, and in that piece compare young men to young women and hopefully get a result that's free of confounding by age, because everybody in that first table was a young person. Then I looked at another table made up of only old people, compared old men to old women. We got a comparison that's also free of confounding by age, because everybody in that table is old. So finally, what stratification does is it then takes an average. It controls for age by taking the odds ratio you had for the young men versus the young women, the 2.3, the odds ratio you had for the old men versus the old women, the 1.6,